Hello, everyone. In your physics class, you've probably been learning a little bit about energy. One of the important aspects of energy is that energy can be stored in a device called a spring. This video is going to teach you a little bit about how to analyze the energy that is in fact stored in a spring that's been stretched. Here is a graph that might look like the graph that you made from data that you collected in your physics class. This is the graph that shows the amount of force needed to stretch a spring to different distances. The distances are on the x-axis, called the displacement, ranging here from 0 to 0.5 meters, and the forces are on the vertical axis, measured in newtons. Notice that the slope of this graph is 200 newtons per meter. This graph is also a straight line, which means we can call it a linear graph, and we can write an equation for this graph in the form y equals mx plus b. For this particular graph, force is on the y-axis, displacement is on the x-axis, and the slope is 200 newtons per meter. So we can fill in those spaces in the equation as shown on the bottom line on the screen. There is no y-intercept here. The y-intercept is 0, so we've left that out of the equation. So this math model, force equals 200 newtons per meter multiplied by displacement, is the equation that describes the relationship between force and displacement for one spring. In physics notation, we would write this as F equals 200 newtons per meter multiplied by delta x. In general, we write this as F is equal to K times delta x, where K is a special value called the spring constant that's different for each spring. The name of this equation is called Hooke's law. So Hooke's law, force equals K times delta x, tells us how force is related to displacement, or the amount that a spring is stretched, and that the constant that relates them is the spring constant. In general, if the spring constant is large, say 1,000 newtons per meter, for example, that means the spring is very hard to stretch. If K is small, for example 5 newtons per meter, that means the spring is easy to stretch. In one way, we can analyze this with the units, noting that 5 newtons per meter means you would have to apply 5 newtons of force to stretch the spring by 1 meter. 5 newtons is about the weight of a calculator. On the other hand, for the larger spring constant, 1,000 newtons per meter, that spring would be very hard to stretch. 1,000 newtons per meter is more than the weight of most people in our classes. But wait, what about energy? We've been talking about force and displacement and spring constant. How does energy fit into this? So springs store what is called elastic potential energy, abbreviated with a capital E for energy and a lowercase el for elastic. This is the type of energy that is stored in stretchy or squishy things. So these are objects like rubber bands or squishable foam or elastic. To find the energy stored in a spring, we're going to use graph area. And so recall from earlier in our course that we've used graph area before. In fact, we've used velocity time graphs, the area of a velocity time graph, to find displacement. Let me show you an example. Here is a velocity time graph that shows an object moving steadily at 8 meters per second. The object moves for 5 seconds. To find the displacement of this object, I would find the area trapped by this graph. That means the area between the graph, shown as the red line at 8 meters per second, and the x-axis, shown at y equals 0. That area would look like this, shaded in pink. Since this is a rectangle, the graph area is just base times height. In this case, that will be 5 seconds multiplied by 8 meters per second for a total of 40 meters. You can see that multiplying and dividing by seconds in the bottom line divides those units away, and we just have meters left. So now let's apply this strategy to our graph for the spring. Here is the same graph that we had before. Notice the slope is 200 newtons per meter. Now this graph is a triangle shape, and the area of a triangle is 1/2 base times height. In this case, that means the graph area will be 1/2 multiplied by the displacement multiplied by the force, where I'm using delta x as the symbol for displacement. So the graph area here will be 1/2 multiplied by 0.5 meters multiplied by 100 newtons. That's the force at the top of the graph. So that graph area has now been shaded in the same pink color. And we see this is 1/2 times 0.5 meters by 100 newtons. That's the same as 0.25 meters by 100 newtons, or 25 meters times newtons. In the call-out box right above the graph, you can see that that's given as 25 newtons times meters. And those numbers are equivalent. Meters times newtons is the same thing as newtons times meters. But what does that mean? What do those units mean? So a graph like this shows 25 meters times newtons of energy, but that is really the same as another unit called a joule, Joule. A joule is just the same as a newton multiplied by a meter. Now that might be unfamiliar to you, so let me compare it to a more familiar unit. 4 joules is roughly equal to 1 calorie. In fact, the exact conversion is closer to 4.186 joules is equal to 1 calorie. This also means that a joule is about 1/4 of 1 calorie. So here is the graph of the same spring, but you can see I've shaded in a smaller area. We don't necessarily have to stretch this spring all the way to 0.5 meters. Perhaps we stretch it a shorter distance, only to 0.2 meters. In that case, you can see that the area of the graph, the area that's shaded in pink, is much smaller than on the previous graph. So let's look at the calculation. Here we remember that graph area is 1/2 base times height. And so now I will take 1/2. The base of this triangle in pink is smaller. It is not 0.5, it's only 0.2. The height here is 40 meters. That's the force at the top of the pink area of the graph. And so 1/2 multiplied by 0.2 multiplied by 40 gives us a total of 4 newtons times meters, or 4 joules of stored elastic potential energy. So the important point about this is that if the spring is not stretched as far, the amount of energy stored is significantly smaller. When the spring was stretched all the way to 0.5 meters, the energy was 25 joules. Here it's only 4, much less. So take a moment now to pause the video and write down the key ideas that you learned from this post-lab video. When you're finished, you can hit play and resume the video. Okay, thank you for writing down your ideas about this video. Let's take a look at some of the key summary points and see how many of them you found. Stretching a spring further requires more force, and that relationship is linear. Springs are different from each other, and each is described by a number called the spring constant. This leads to an equation called Hooke's law. Force is equal to K times delta X, where the constant K is what's known as the spring constant. The larger the value of K, the harder a spring is to stretch. Springs store energy, and the amount of energy can be calculated using graph area. Energy is measured in a unit called the joule, abbreviated capital J, and this is the same unit as newtons multiplied by meter. Okay, I hope that you learned many of those key points. Please go back and review the video if it helps to understand some of them more clearly. And don't forget that you can always send questions to your instructor by email. Thanks for watching. Good luck with your physics class.